Good afternoon, good morning, wherever you are in the world. And welcome to the AfricaNEV podcast, where we talk about sustainable energy and transport for Africa. My name is Gad Senyejom Ashiabo, and today I am here with Olukokun. Introduce yourself.
Hi, my name is Olukokun. I'm a Nigerian and I'm proud to be an African. Yeah.
And from Kenya, the billionaire next door.
Hey, billionaire, really? I'm not sure about that, but thank you for your prayers. I'm John Singo. I'm in Nairobi, Kenya.
Okay. And the battery Don. Please introduce yourself.
This is all right. I'm Elliot from Accra.
I think your connection is bad.
Yeah, Elliot's internet has refused. It said no.
I have a lot as far as vehicles go, and it's a pleasure to be here with all you great guys.
But today our special guest is the beautiful Wacera Wambugu.
Wacera Wambugu. It's okay.
Wacera. It's Wacera. Please, I want to be corrected. It's Wacera Wambugu.
Yes, Wambugu, yes.
Yeah, and our topic is quality standards and energy access in Africa. And welcome to the AfricaNEV podcast.
Thank you. Yeah, and I can see some people in the workshop. I really miss that. How are you in the workshop with Corona?
Well, you see, the good work has to continue, not minding Corona or not, but we are taking all the precautions, you know.
Okay. Yeah, good to see some people are actually doing something during this time.
Anyway, Anne, so can you sort of introduce yourself to us and give us a little bit of your
So my name, as you've been told, is Wacera Wambugu, and I'm an electrical engineer. I guess already introduced myself. I work in the quality and standardization component of electrical systems, so electrical generally. That's my general work. So as we continue, maybe I'll talk a bit more about what exactly I do in each of those areas.
So,
okay.
Can you tell us about DC standards in Africa? Why do we need standards? DC standards.
Okay. So I'm going to start with a short story that one of my mentors likes telling. So he likes talking about why AC actually ended up being the common electricity type that we use. So for those who are listening, AC is alternating current, which is the other type of electricity that exists aside from direct current. So one of the reasons was because of problems in transmission. For DC, how far you can transmit is very limited, and also I guess one of the second reasons was if you Google war of current, you should be able to see quite a bit of information about how that transpired. But fast forward to today, DC systems, DC has come a long way. We have we have a lot of capacity. There's someone who's we have a lot of capacity we have a lot of I'd say innovations that have happened in the DC world. So DC to DC converters have come a long way. You can transmit DC also on a longer distance. I'm still trying to avoid using like extremely technical terms. So there's a lot of progress that has been made in terms of DC, and I guess the final nail on that progress is the fact that most distributed renewable energy systems, that's solar, wind, you actually produce DC. So what we're doing right now, and also most of our appliances are DC. I know most people do not really realize that. So what we do, when you put a solar PV system on your house and you're using it 100%, what you're doing is you take a DC production, so you're producing solar, yeah, and then you convert it to AC using an inverter, and then you use a rectifier to actually convert that AC back to DC, so that you use it to supply. Yeah. So what we're doing is DC, AC, AC, DC, which does not make sense. We end up losing a lot of power in the middle, but that's mostly because of the way our systems have been designed. Because if you want to, for example, buy a DC plug to actually charge your phone with, the best you can do normally tends to be the USB plug that you can use to input to your phone. So the world is not designed, a lot of the world is not designed with DC in mind, I'd say, and we need to shift that and actually change, the way designing itself is done.
Wait, but what you are saying, if I'm getting you correctly, is that in the old system, our power plants will produce DC, then convert to AC for transmission. Then when it gets to with the consumers for transmission and distribution, then at the consumer end, the devices we have are DC. So the AC now has to be converted back to DC with subsequent power loss in between the conversion value chain, right? Now you are saying, I'm just trying to understand what you are saying clearly and we explain that when it comes to this whole renewable energy space, which you are generating DC. So if you're generating DC in your house from solar, there's no need to convert to AC before you can reconvert to DC for your phone to use.
Yes.
You can just take the AC directly and
the DC directly and actually charge your phone. But that would require a lot of infrastructure to change, which I guess is something that when I talk to engineers a lot these days, I like telling them that electrical engineering is changing. It has changed actually. Electrical engineering used to be you get employed in some grid in some company that's doing grid provision. And then, the power provider, and then you wake up every day, you go to a transmission, you go to a substation or to do something. But electrical engineering is changing with the advent of renewable energy systems. And for us to actually make use of it by 100%, we'll also need to change the way the way our electronics are structured, which is why standardization comes in very importantly, because I'd say, like I said, the main problem is that the world is designed for AC. So we need to redesign the world in a way that, I'm not saying we're about to kick out the AC any soon, that's not going to be easy, but we need to be able to buy, when you're buying your laptop, you should be able to be given an AC adapter and also a DC adapter, right? But to do that, we need to standardize DC, because right now DC is the Wild West. So you'll find 48, 24, 12 volts, everyone is using every single different type of voltage. There's all these different things that will need to be done. So in terms of standardization of the DC voltages, so that we're all able to use, maybe we might not end up with a system where we use one plug, right? We might have different plugs, but at the end of the day, it should be possible for someone to maybe either buy 2 plugs with their laptop, but also maybe buy an extra plug for DC just in case they'll do a PV installation or something like that. So there's some countries which are actually experimenting with a DC grid, but that's also, I guess that's something that's, I'm waiting to see where this goes. It seems we are where I'd say Steve Jobs was with the iPhone, with electricity right now. There's a lot to be done. Yeah.
Before we continue, you made allusions to a DC grid, transmission grid. Okay. But for now, most of the devices, in fact, almost all, use DC. So why do we need a different standard? Because if I'm using an iPhone, I know that I'm using an iPhone connector, or maybe USB Type-C. If I'm using an Android, I know that this is Android connector. The voltages are well defined.
Yes.
So what standardization are you talking about again for this DC equipment?
Cabling. The cable that goes into your laptop right now, the cable that goes into your PV system, as in the cables, the voltages that let me start there. So there's DC voltages, right? Like I've said, the guy who's in the workshop right now,
Olukokun.
So do you have, how many DC voltage types do you install? Like if you're to install in a household, how many voltages, different voltage configurations do you have?
For my household or for the workshop? I don't understand.
Do you install solar or something like that for anyone?
No, not for
okay.
now.
I can answer that.
John can speak to that. And then Patrick also speaking about that.
Yeah.
So basically, you have the 12 volts, 24 volts.
Yes.
So
there's all this, Sorry, there's all these different configurations, and right now, aside from having all these different configurations, there's the way DC systems are set up. So let's say you want to install a PV system on top of your roof, right? And this time round, you have enough money to be able to install enough electricity to power, let's say, bulbs in your house. And then you install that. So probably you're going to install a 12 volt DC system. And then next time you want to power a larger, because I think then what I'm talking about is this is where I like telling engineers where our innovation meets reality, which is the fact that not everyone will afford to maybe put out, to install a big 48 volt system, right? So the next time the person who installed the system that powers a light bulb wants the next level. They want something to power their TV, their whatever, and then now they want to add. And remember that for solar PV systems, you can't just stack solar panels. So the solar panels that you bought at the same time are the only ones that you're going to be able to use with that lot. So the next time when you're coming to buy new solar panels, you'll need to buy a new set and then buy a new set of controllers. So there's a need, for example, I know there's a group called Open DC Grid that's looking at, if you install all these different PV systems, is there a way to network the charge controllers so they can be able to speak to each other? So in case you want, because as you install all these different PV systems, you will have extra amounts of energy that you're not using over time. Because even if you install one panel and you put a couple of bulbs, you'll still have there's some extra electricity that you're not using. So the aim here is, if you can be able to install, based on the money that you have, every single time you install something, over time, just to see, can these charge controllers speak to each other so that you're able, and I've noticed that I've used the word charge controller. A charge controller is what is put in between a solar panel and a battery to just make sure that, to control the voltage, because then there'll be, intermittency in the solar panel, but you need to have like a constant output voltage and also current. So it does like a bunch of things, but I'm going to speak to just talk about that. So the standardization is in terms of these things. So number one, right now, if you're to go to a shop and buy your laptop, right, they're not going to give you a DC plug. You'll only get an AC plug, the one that you connect to your wall. The problem with that is that if you want to create a DC plug, you'll need to know, let me say, what voltages your
equipment can take.
Yeah, your equipment can take, right? So you'll find that some of them are at 19 volts. Sometimes you find that the input is 19, sometimes it's 15, sometimes. So that's the standardization that needs to happen. We need to have universal input voltages,
okay,
currents, and all these different things for different appliances. So that if your phone, if you're talking about phones, an iPhone, an Android phone, all of them have like a similar voltage and current that they take. Then at that point, we can now say, okay, now let's standardize the source. So let's say you can use, there's a 48 volt to 12 volt plug, that, and you say, oh, most computers use 12 volts. But right now, anyone who's every single DC appliances, which is everything that we do, it has its own voltages depending on what the manufacturer wanted to do with it and all these different things. I'm not saying it's going to be easy standardizing this, because there's reasons in terms of, for example, power consumption. So someone else will do 19 volts versus 12 volts because then they need, they need a certain type of, they need a certain amount of power in their system. So what we'll be telling them if you decide to standardize is, well, you need to ensure that your system actually fits into this kind of, narrow, I guess, scope, which is use 12 volts. And then someone will tell you, no, mine needs 19 volts. So I think that's where the standardization thing needs to come in.
Okay, as we are talking, I am just seeing more and more money. Before you continue, Olukokun has raised his hand. So he wants to come in. I saw Patrick too on the call. He deals in EV charging systems, because these are people who are from the production perspective, so that they can bring their perspective. Olukokun, please, you have the floor. You want to say something?
Johan, I will have to draw you back a little. I wanted to understand some of the things you said. In my basic knowledge of electrical engineering, I studied mechanical engineering, and we have to borrow from electrical department. Yes, I think there are quite some advantages, because when you mentioned the DC grid, then I begin to look into, okay, what are the advantages of AC over DC? I think AC could travel a far distance at a very good speed, and that is why it is good to, it is preferred, so to say, to DC when it comes to having a grid. So you have a station to generate, then you can use your cabling to, the grid to do the transmission and all of that, and everybody. I think that's one of the advantages over DC. So and when you mentioned the the grid for DC, I'm beginning to wonder how effective that would be. How much power are we going to generate to be able to put it on a grid? And I was like, okay, probably the best solution for that would have been a mini grid. And like I was saying on the group sometimes ago, that in Nigeria, power generation is the sole business of federal government. And even if you buy transformer, if you buy cabling to wire up your house, so far they put their power on it, everything has become the property of the government, and which is really making us to lack a lot in this infrastructure, because I don't mean they can license, private organizations, individuals to generate their own power. We will not be in the situation we are in Nigeria currently. So I think mini grid will be a good example. But if you are now comparing, I need you to shed more light. Are you trying to compare the kind of grid we have for AC for the grid that you said some people are working on? That's my number one.
Okay, please hold on to that thought. Two things. First of all, Anne initially spoke about DC grid transmission versus AC grid transmission. But that topic, she introduced it and then she shelved it. The focus now is in the DC equipment. She's talking about the equipment. You see, this is relevant because we are about to talk about cars too, which are all DC. You understand? We're talking about energy, which are all DC. So her question was, or her statement was, that those who are manufacturers like you, what you are doing, your equipment, based on the requirements of your device, okay, you can choose an arbitrary input voltage and current. I hope you understand what I'm saying. Because you know that when you plug into your grid in Nigeria, you use 240 volt, just like Ghana. And I don't know what current. Okay. So you know that this is what you are getting. And and then you have your rectifier or transformer, whatever, to convert into the required voltage that your equipment needs. I hope you understand what I'm saying. So she is asking that maybe people like you, who are the ones generating the equipment, if you can also talk about your perspective in terms of what inform the voltages and currents you choose, apart from the requirements of the equipment, because she wants us to go to a world where if it's DC of this equipment of this size, we are using a particular voltage. Do you get what I'm saying? So tomorrow I can manufacture a cable and anybody, you can buy and slot it into your equipment. You don't have to think about it. You know that this particular type of category of cable, this is the voltage you expect, this is the current you expect. Am I on point?
Yes. So just to add something. So when I say the grid, and this is one of the things that I was saying at the beginning, electrical engineering is changing. So maybe I'll expand on that a bit in a second, but just to add to what you've said, the reason why the world has progressed as much as it has progressed today is because you don't need to really concern yourself a lot when you're going to buy an appliance, starting asking yourself questions about, will this fit into my house? Do I need to know the voltage? For the common man, that's not information they'll have. So what you just need to do is buy an appliance, come and plug it into your socket. And people, I think, a lot of people underestimate the power of that. Being that
interoperability.
So interoperability. Again, now I'm moving into using the words that we use in our section.
No, once you understand the meaning, it's okay.
Yes. So interoperability is very, very important, that you will go to the market, you will buy an appliance, you won't have to think whether it will fit into your system or not, and you will come and plug it into your wall and it will work. You understand? So that is the place where the DC world needs to go. In terms of transmission, actually, Kenya is doing a high voltage DC system between here and DC. Yeah. So there's a transmission because it's come that long. Like I mentioned, DC has changed. DC has changed so much, and maybe because I'm on the committee for DC that's supposed to be doing the standardization of these things, I'm a bit biased, but DC has come a long way. The technology has improved so much. One of the reasons why we even have a charge controller is because DC has changed a lot. And
please,
because
hold your thoughts.
Okay.
So you were talking about the DC. I mean, please continue. You are making a point.
Okay, yeah, I was trying to say something. So maybe the best place to start is to explain how electrical engineering is changing, so that all of us know why I have the train of thought that I have. So like I said, in the past, if you're an electrical engineer, your main job would have been to maybe get employed by a company that's, that produces power. So a power generation company or a transmission company or distribution company. And then your job would be probably doing some things within the aspect. So in that sense, that traditional sense of a grid is still there. So today, for example, the Kenyan government has expanded the national grid a lot. I think we have 75% coverage right now. And the thing about that kind of expansion is that it's not yet, it's not yet gone, and it has its place. The only problem is that the traditional sense of electrical engineering fails where we talk about climate change. There's all these problems that we're going to experience thanks to climate change. So we're going to see more wildfires, for example, like the ones you've seen in California, if you've managed to actually watch news. We're going to see more floods. So we're going to have a lot more problems if we just depend on this traditional sense of a grid, which, like I said, has its place. Yeah. So for this traditional sense of a grid, there's as the government has expanded electricity in Kenya, we've seen a greater interest arise for people to connect appliances, and that's the thing that the traditional grid offers that most other decentralized systems do not offer. Like, because the electricity is kind of, and I'm gonna put quotes, unlimited, right? You can buy any appliance, you'll buy a fridge, whatever, without having to worry about if the energy that you're getting from your grid provider is enough to actually power the appliances. Yeah. And then there's the second aspect of electricity that's changing, which is now we're talking about decentralized systems. So decentralized systems worldwide. So there's all these kinds of renewable energy systems that are coming online, and there's different things to be done under that. Yeah. So you have a connection for rural communities. You have people who are using it for backup. Yeah. In our case, for example, for Africa, in case where our grid providers decide to switch us off in the middle of the day, and you have a lot of meat. Yeah, right, KPLC. So you have a lot of meat in your fridge, like me. There was a day I had to boil all my meat. So you have a lot of meat in your fridge, and then it will go bad. So some people are installing backup systems. So that's where distributed renewable energy systems come in. And then I guess the final one and the one that I think a lot of people I'd say a lot of people do not think about a lot is this, I'd say, this DC revolution that's happening. Yeah, in that in the past maybe we would not even be having this conversation, right? So we have if I was to describe electricity to you right now, I would say there is the grid as was, as is, as will remain, right? Then there is the conversation that's going on around renewable energy systems, and this time around we're talking about distributed renewable energy systems. They're more resilient when it comes to climate change, because then they're decentralized. If your neighbor's pole falls, if as long as it doesn't fall on your house, you still have electricity, right? And then, like I said, in the DC world, there's all these different things that are happening, all the way from conversations regarding high voltage DC transmission, like the one that's happening in Kenya, but all the same, there's a lot more, there's a lot more content in that space. So electrical engineering is not what we knew. It's not what we were taught in school. The principles are still the same. It doesn't change. It's still the same physics. It's still the same Maxwell's equations still remain. The only thing that's changing is in how we actually use it, how we interact with it. And the most challenging bit of these new systems that are coming online is the fact that they need the customer to actually understand what's happening with the system. And that's why standardization comes in, because we need to remove that need. The same way you do not need to think about how your electricity gets to your house, what voltage your electricity is at your socket, what current, how much energy you actually have. That's because of standardization. We need to remove the need for people to actually know complex things that they do not need to know when it comes to DC systems.
I think that.
I'm going to ask the second question before that.
Okay, please continue.
Mm-hmm.
Explain what he did. See, when we had this little break to reconnect, I had to, ruminate with my team member here about this standardization and how we think it could work out on the part of engineering. Mm-hmm. And the question will be that, how far have you gone with this standardization and the advocacy? Because I will take it as an advocacy right now. Because on the part of engineering, it is possible, but it's difficult for you to have a supply of a particular voltage and current in DC format.
Yes.
And you now put up any kind of appliances. Now, what we found so very easy is that once AC is coming, you can easily rectify it to any voltage you want, and your appliance connect and everything works fine. When it comes to DC, it's not usually easy to bring it down to another voltage for the appliance or bring it up for the appliance. That is why most people rely on rectifying the 220, 240 volts coming up to the particular voltage of DC you want. I know you are worried about the losses. There are a lot of losses, fine. But how far have you gone with this standardization advocacy? Do you think it's achievable in a quick time?
Yeah. So what you're talking about, changing one DC voltage to the other is something that has been sold for a very long time. DC to DC converters have existed for a while now, and that's the technology I'm trying to say. There's a bunch of technologies that have come on board that were not there years ago, right?
Yeah.
So right now, for example, changing your DC voltage from 24 to 12 is not going to be is not a massive problem. The biggest problem that we have is in terms of the supply. Let me call it the quantity of supply. So for your coming from your KPLC, whichever part of the world you're from, coming from your KPLC, that quantity is unlimited, right? But for most DC systems, seeing as a solar panel generator is not going to compete with a genset that's on a hydro dam, right? There's a limit to how much energy you can get out of a solar panel at any given point. So that's the challenge. So that's why we're saying a lot of people, if you're to actually power every appliance, and I know one of my friends from the UK thinks this is a nightmare. The way I see it is that people will be able to buy a solar panel and an appliance, So you'll be able to stack them. So instead of you wanting to install a massive PV system, right? You install one big one and then you get all your electricity from it. You can decide and buy small chunks of it as you go, right? And then at the end of the day, you have one big system. The thing is, when you do small chunks, what you end up doing is there's a small amount of electricity in each of them that will not be used. You understand? As you know, PV systems will charge, so probably your battery will charge, this one will charge and it will fill up, that one will charge and it will fill up, the other one will charge and it will fill up. So one of the things that is crucial to try and see is there a possibility to actually network these systems that you have so that they're able to maybe, let me say, if they're all network, let's assume, and that's the other thing that has changed. Actually, I forgot to add that information technology as a whole, as a sector, is part of the reason why electricity will get revolutionized, right? Because when these things are communicating with each other, you can make them communicate with a solar water pump and say, during the day, instead of you charging each of those things separately, right? So just do trickle, charge a bit, but then redirect a good amount of the power to a solar water pump that's pumping something in the farm. So the communication component of it is crucial. It's one of the things that I think people really need to figure out in terms of making DC work. How you can get different DC systems to communicate with each other. So someone is not limited to buying one that they can afford, which is what's happening right now, but they can buy their system in small components as they go and be able to network all of them in a way that they can use any extra energy that comes out of it to do something else useful during the day.
Okay, I think that, you see, what Anne is saying, the best way to understand it is from the monetary point of view. All right. So in terms of translating what she's saying, one way to look at it is to say that, okay, if you are designing a motor, then you need 12 volts, 6 amp current. Okay, 12 volts voltage and 6 amps current. Now, if there's a DC wiring standard that, okay, there are cables that have 14 volts, 8 amps. All right. You, Olukokun, you can go and buy that cable and use it for your application. We are not going to use the entire 14 volts. Your equipment is going to use 12 volts out of the potential 14 that cable can carry. Are you with me, John? Okay. Now, what this means is that the manufacturer of this equipment can produce more of that wire at scale, which means that it will be cheaper to produce. Because it is cheaper to produce, in terms of affordability, it will be cheaper for all of us to buy. Okay. Now, in terms of design tool, if you are going to design this motor, you don't have to now figure out how to buy this extra rectifier, step down transformer, all this extra equipment you have to now incorporate in your design are gone. You just need one wire. Plug it in, and you are going. So the final cost of your product will be cheaper. You make more money. You'll be more efficient because you can produce more of that thing without having to invest more capital. Everybody is happy, except those who have made it their job to profit on complexity. This thing, yes, this thing, it is the reason why today our personal devices, they are being an explosion of phones, computers, and all that. This is the reason why. Okay, so what Anne is saying is basically how we can actually make money and control our destiny, if you will, as a continent. Yes, but now, I think I wanted to switch to the gist of the matter, okay? Because we're talking about standardization, but then who defines the standards? Because the person who defines the standard is the one actually controlling everything.
Yeah.
Okay, so we are going to talk about that, but first of all, let's talk about Africa. You have been working on this standards thing for some time now. You are the chair, the African chair. I cannot pronounce the whole title. Maybe you can help
African
me.
Electrotechnical Standardization Commission.
Good.
Yeah.
You're a big woman, very big woman, an angry and big woman. Okay, so how? Okay, first of all, why must we standardize across the continent?
Okay.
Why not? Oh, Patrick, you are back. I was waiting for you. Please continue.
Yeah,
John,
sorry, I had to put the baby to bed.
Okay.
Father of the year.
Anyway, Anne, sorry. The reason why I'm acknowledging Patrick is because Patrick works on EV chargers. So he is a direct consumer of your product. All right.
Okay. Patrick, I can see Patrick. Who's that exactly?
I think AfricaNEV.
Ah,
You see
okay.
AfricaNEV, that's his company. Okay. So it's very, very important that he is here, he and Elliot. That's why I'm actually taking the time to acknowledge him. So please, Anne, please can you continue? Why must we have a standard across Africa, not only Kenya?
So I'm going to move towards the money, because then I've noticed that you guys like talking about the money a lot.
No, because the money is what to motivate a lot of people. You see, Africa it's like somebody talking about climate change. They are not interested. Maybe they can see the benefits.
So I'm going to first of all mention why you should care if your electricity is decentralized or not in terms of money. Like I said, you're going to get we're going to see more floods. We're going to see more rain. I know you've probably seen it in your country. So things are just getting extreme by the day. So every time that infrastructure falls, number one, you're in darkness for a couple of days. And you see, in other countries, in Western countries, when the infrastructure goes down, it's a couple of days and then the government has fixed it. Here in Kenya, if your entire line falls,
John Misingo.
big problem.
There's another witness now.
So that means that for one, you'll be in darkness. right? And then on top of that, who do you think will pay for the cost of replacing that line when it gets replaced? That's after 3 months or 4 months or even a year. I've seen places where they came and erected poles and then just left. And then, yeah.
Your case will not be worse than that of Nigeria.
I was going to say that. I was going to say that at least they have light. You don't have light.
So the main problem is that every single time our infrastructure goes down, every single time it's put back up, we'll pay with it using our electricity bills. Kenyans know that very well because Kenyans are right now paying for something called the Last Mile Connectivity Project. So the Last Mile Connectivity Project is what took Kenya from 30% connection rate to 75%. So the Kenyan government actually connected a lot of places in the country using that project. The problem is, I think when it was being done, none of us actually understood the implications of the government expanding. Yeah, because you see, now we are paying for it in our bills. And the other day, I think our bills just got increased. So, and everyone is complaining, and I'm asking them, guys, did you think the electricity expansion was going to be free?
John,
what did you think was going to be free?
John, I think I will do the part 2 of our conversation, and Anne must be there. It will be you and Anne. So for those of you watching on YouTube or whatever, we had a conversation with John. This part 1, so you can watch. Yeah. Look at my finger, either this direction or this direction. You will watch the link to the other video. The Kenyans want their service provider to be switched off. So they just switch off KPLC. So that they know that they are in darkness. Yes. It's a whole campaign.
The problem, I think I'm normally on the fence on this one because I work in an academic institution. So I understand the challenges they're going through. But at the same time, I know that it's not engineers who are in charge in that Kenya Power. They've put some very political figures there. Them, they're just eating, you know? Anyway, that's a conversation for a different day.
For another day.
Yeah. The point
John, we cannot be having our dirty line here. We need to be sure of what our problem is. And this is not alone.
No.
It's Africa.
No.
Don't know where we are.
Please. Before we
okay, so let me continue.
Before we go side, please.
Yeah.